In a spark ignition engine, the ignition system provides a spark that ignites the fuel-air mixture in the cylinders and is made up of magnetos, spark plugs, high-tension leads, and the ignition switch. A magneto uses a permanent magnet to generate an electrical current completely independent of the aircraft's electrical system. The magneto generates sufficiently high voltage to jump a spark across the spark plug gap in each cylinder. The system begins to fire when the starter is engaged and the crankshaft begins to turn. It continues to operate whenever the crankshaft is rotating. Most standard certificated aircraft incorporate a dual ignition system with 2 individual magnetos, separate sets of wires, and spark plugs to increase reliability of the ignition system. Each magneto operates independently to fire one of the 2 spark plugs in each cylinder. The firing of 2 spark plugs improves combustion of the fuel-air mixture and results in a slightly higher power output. If one of the magnetos fails, the other is unaffected. The engine will continue to operate normally, although a slight decrease in engine power can be expected. The same is true if one of the 2 spark plugs in a cylinder fails. The operation of the magneto is controlled in the flight deck by the ignition switch. The switch has 5 positions: 1 off, 2 R right, 3 L left, 4 both, and 5 start. With right or left selected, only the associated magneto is activated. The system operates on both magnetos with both selected. A malfunctioning ignition system can be identified during the pre-takeoff check by observing the decrease in RPM that occurs when the ignition switch is first moved from both to right and then from both to left. A small decrease in engine RPM is normal during this check. The permissible decrease is listed in the AFM or POH. If the engine stops running when switched to one magneto, or if the RPM drop exceeds the allowable limit, do not fly the aircraft until the problem is corrected. The cause could be fouled plugs, broken or shorted wires between the magneto and the plugs, or improperly timed firing of the plugs. It should be noted that no drop in RPM is not normal, and in that instance, the aircraft should not be flown. Following engine shutdown, turn the ignition switch to the off position. Even with the battery and master switches off, the engine can fire and turn over if the ignition switch is left on and the propeller is moved, because the magneto requires no outside source of electrical power. Be aware of the potential for serious injury in this situation. If this occurs, the only way to stop the engine is to move the mixture lever to the idle cutoff position, then have the system checked by a qualified aviation maintenance technician. The engine oil system performs several important functions: lubrication of the engine's moving parts, cooling of the engine by reducing friction, removing heat from the cylinders, providing a seal between the cylinder walls and pistons, and carrying away contaminants. Reciprocating engines use either a wet sump or a dry sump oil system. In a wet sump system, the oil is located in a sump, which is an integral part of the engine. In a dry sump system, the oil is contained in a separate tank and circulated through the engine by pumps. The main component of a wet sump system is the oil pump, which draws oil from the sump and routes it to the engine. After the oil passes through the engine, it returns to the sump. In some engines, additional lubrication is supplied by the rotating crankshaft, which splashes oil onto portions of the engine. An oil pump also supplies oil pressure in a dry sump system, but the source of the oil is located external to the engine in a separate oil tank. The oil pressure gauge provides a direct indication of the oil system operation. It ensures the pressure in pounds per square inch, PSI, of the oil supplied to the engine. Green indicates the normal operating range, while red indicates the minimum and maximum pressures. There should be an indication of oil pressure during engine start. The oil temperature gauge measures the temperature of the oil. A green area shows the normal operating range, and the red line indicates the maximum allowable temperature. Unlike oil pressure, changes in oil temperature occur more slowly. This is particularly noticeable after starting a cold engine, when it may take several minutes or longer for the gauge to show any increase in oil temperature. Check oil temperature periodically during flight, especially when operating in high or low ambient air temperature. High oil temperature indications may signal a plugged oil line, a low oil quantity, a blocked oil cooler, or a defective temperature gauge. Low oil temperature indications may signal improper oil viscosity during cold weather operations. The oil filler cap and dipstick for measuring the oil quantity are usually accessible through a panel in the engine cowling. If the quantity does not meet the manufacturer's recommended operating levels, oil should be added. The AFM POH or placards near the access panel provide information about the correct oil type and weight, as well as the minimum and maximum oil quantity. The burning fuel within the cylinders produces intense heat, most of which is expelled through the exhaust system. Much of the remaining heat, however, must be removed or at least dissipated to prevent the engine from overheating. Otherwise, the extremely high engine temperatures can lead to loss of power, excessive oil consumption, detonation, and serious engine damage. While the oil system is vital to the internal cooling of the engine, an additional method of cooling is necessary for the engine's external surface. Most small aircraft are air-cooled, although some are liquid-cooled. Air cooling is accomplished by air flowing into the engine compartment through openings in front of the engine cowling. Baffles route this air over fins attached to the engine cylinders and other parts of the engine, where the air absorbs the engine heat. Expulsion of the hot air takes place through one or more openings in the lower aft portion of the engine cowling. The air cooling system is less effective during ground operations, takeoffs, go-arounds, and other periods of high-power, low airspeed operation. Conversely, high-speed descents provide excess air and can shock cool the engine, subjecting it to abrupt temperature fluctuations. Operating the engine at higher than its designed temperature can cause loss of power, excessive oil consumption, and detonation. It will also lead to serious permanent damage, such as scoring the cylinder walls, damaging the pistons and rings, and burning and warping the valves. Monitoring the flight deck engine temperature instruments will aid in avoiding high operating temperature. Under normal operating conditions, in aircraft not equipped with cowl flaps, the engine temperature can be controlled by changing the airspeed or the power output of the engine. High engine temperatures can be decreased by increasing the airspeed and/or reducing the power. The oil temperature gauge gives an indirect and delayed indication of rising engine temperature, but can be used for determining engine temperature if this is the only means available. Most aircraft are equipped with a cylinder head temperature gauge, which indicates a direct and immediate cylinder temperature change. This instrument is calibrated in degrees Celsius or Fahrenheit and is usually color-coded with a green arc to indicate the normal operating range. A red line on the instrument indicates maximum allowable cylinder head temperature. To avoid excessive cylinder head temperatures, increase airspeed, enrich the mixture, and/or reduce power. Any of these procedures help to reduce the engine temperature. On aircraft equipped with cowl flaps, use the cowl flap positions to control the temperature. Cowl flaps are hinged covers that fit over the opening through which the hot air is expelled. If the engine temperature is low, the cowl flaps can be closed, thereby restricting the flow of expelled hot air and increasing the engine temperature. If the engine temperature is high, the cowl flaps can be opened to permit a greater flow of air through the system, thereby decreasing the engine temperature. Most small aircraft use a direct cranking electrical starter system. This system consists of a source of electricity, wiring, switches, and solenoids to operate the starter and a starter motor. Electrical power for starting is usually supplied by an onboard battery, but can also be supplied by external power through an external power receptacle. When the battery switch is turned on, electricity is supplied to the main power bus bar through the battery solenoid. When starting an engine, the rules of safety and courtesy should be strictly observed. One of the most important is to make sure there is no one near the propeller. In addition, the wheels should be chalked and the brakes set to avoid hazards caused by unintentional movement. To avoid damage to the propeller and property, the aircraft should be in an area where the propeller will not stir up gravel or dust. During normal combustion, the fuel-air mixture burns in a very controlled and predictable manner. In a spark ignition engine, the process occurs in a fraction of a second. The mixture actually begins to burn at the point where it is ignited by the spark plugs, then burns away from the plugs until it is all consumed. This type of combustion causes a smooth buildup of temperature and pressure and ensures that the expanding gases deliver the maximum force to the piston at exactly the right time in the power stroke. Detonation is an uncontrolled explosive ignition of the fuel-air mixture within the cylinder's combustion chamber. It causes excessive temperatures and pressures, which if not corrected can quickly lead to failure of the piston, cylinder, or valves. In less severe cases, detonation causes engine overheating, roughness, or loss of power. Detonation is characterized by high cylinder head temperatures and is most likely to occur when operating at high power settings. Common operational causes of detonation are use of a lower fuel grade than that specified by the aircraft manufacturer, operation of the engine with extremely high manifold pressures in conjunction with low RPM, operation of the engine at high power settings with an excessively lean mixture, maintaining extended ground operations or steep climbs in which cylinder cooling is reduced. Detonation may be avoided by following these basic guidelines during the various phases of ground and flight operations. Make sure the proper grade of fuel is used. Keep the cowl flaps, if available, in the full open position while on the ground to provide the maximum airflow through the cowling. Use an enriched fuel mixture as well as a shallower climb angle to increase cylinder cooling during takeoff and initial climb. Avoid extended, high-power, steep climbs. Develop the habit of monitoring the engine instruments to verify proper operation according to procedures established by the manufacturer. Pre-ignition occurs when the fuel-air mixture ignites prior to the engine's normal ignition event. Premature burning is usually caused by a residual hot spot in the combustion chamber, often created by a small carbon deposit on a spark plug, a cracked spark plug insulator, or other damage in the cylinder that causes a part to heat sufficiently to ignite the fuel-air charge. Pre-ignition causes the engine to lose power and produces high operating temperature. As with detonation, pre-ignition may also cause severe engine damage because the expanding gases exert excessive pressure on the piston while still on its compression stroke. Detonation and pre-ignition often occur simultaneously, and one may cause the other. Since either condition causes high engine temperature accompanied by a decrease in engine performance, it is often difficult to distinguish between the two. Using the recommended grade of fuel and operating the engine within its proper temperature, pressure, and RPM ranges reduce the chance of detonation or pre-ignition. The fuel system is designed to provide an uninterrupted flow of clean fuel from the fuel tanks to the engine. The fuel must be available to the engine under all conditions of engine power, altitude, attitude, and during all approved flight maneuvers. Two common classifications apply to fuel systems in small aircraft: gravity feed and fuel pump systems. The gravity feed system utilizes the force of gravity to transfer the fuel from the tanks to the engine. For example, on high-wing airplanes, the fuel tanks are installed in the wings. This places the fuel tanks above the carburetor, and the fuel is gravity-fed through the system and into the carburetor. If the design of the aircraft is such that gravity cannot be used to transfer fuel, fuel pumps are installed. For example, on low-wing airplanes, the fuel tanks in the wings are located below the carburetor. Aircraft with fuel pump systems have two fuel pumps. The main pump system is engine-driven with an electrically driven auxiliary pump provided for use in engine starting and in the event the engine pump fails. The auxiliary pump, also known as a boost pump, provides added reliability to the fuel system. The electrically driven auxiliary pump is controlled by a switch in the flight deck. Aviation gasoline, avgas, is identified by an octane or performance number, which designates the anti-knock value or knock resistance of the fuel mixture in the engine cylinder. The higher the grade of gasoline, the more pressure the fuel can withstand without detonating. Lower grades of fuel are used in lower compression engines because these fuels ignite at a lower temperature. Higher grades are used in higher compression engines because they ignite at higher temperatures, but not prematurely. If the proper grade of fuel is not available, use the next higher grade as a substitute. Never use a grade lower than recommended. This can cause the cylinder head temperature and engine oil temperature to exceed their normal operating ranges, which may result in detonation. Since use of the correct fuel is critical, dyes are added to help identify the type and grade of fuel. Fuel should be drained from the fuel strainer quick drain and from each fuel tank sump into a transparent container, and then checked for dirt and water. Water is the principal fuel contaminant. Suspended water droplets in the fuel can be identified by a cloudy appearance of the fuel or by the clear separation of water from the colored fuel, which occurs after the water has settled to the bottom of the tank. As a safety measure, the fuel sumps should be drained before every flight during the pre-flight inspection. Most aircraft are equipped with either a 14 or a 28-volt direct current electrical system. A basic aircraft electrical system consists of the following components: alternator, generator, battery, master battery switch, alternator, generator switch, bus bar, fuses and circuit breakers, voltage regulator, ammeter, loadmeter, associated electrical wiring. Engine-driven alternators or generators supply electric current to the electrical system. They also maintain a sufficient electrical charge in the battery. Electrical energy stored in the battery provides a source of electrical power for starting the engine and a limited supply of electrical power for use in the event the alternator or generator fails. During operations at low engine RPM, the electrical needs must be drawn from the battery, which can quickly be depleted. Alternators have several advantages over generators. Alternators produce sufficient current to operate the entire electrical system, even at slower engine speeds, by producing alternating current, which is converted to direct current. The electrical output of an alternator is more constant throughout a wide range of engine speeds. The electrical system is turned on or off with a master switch. Turning the master switch to the on position provides electrical energy to all the electrical equipment circuits except the ignition system. A bus bar is used as a terminal in the aircraft electrical system to connect the main electrical system to the equipment using electricity as a source of power. This simplifies the wiring system and provides a common point from which voltage can be distributed throughout the system. Fuses or circuit breakers are used in the electrical system to protect the circuits and equipment from electrical overload. Spare fuses of the proper amperage limit should be carried in the aircraft to replace defective or blown fuses. Circuit breakers have the same function as a fuse, but can be manually reset rather than replaced if an overload condition occurs in the electrical system. Placards at the fuse or circuit breaker panel identify the circuit by name and show the amperage limit. An ammeter is used to monitor the performance of the aircraft electrical system. The ammeter shows if the alternator generator is producing an adequate supply of electrical power. It also indicates whether or not the battery is receiving an electrical charge. Ammeters are designed with the 0 point in the center of the face and a negative or positive indication on either side. When the pointer of the ammeter is on the plus side, it shows the charging rate of the battery. A minus indication means more current is being drawn from the battery than is being replaced. A full-scale minus deflection indicates a malfunction of the alternator generator. A full-scale positive deflection indicates a malfunction of the regulator. Another electrical monitoring indicator is a load meter. This type of gauge has a scale beginning with 0 and shows the load being placed on the alternator generator. The load meter reflects the total percentage of the load placed on the generating capacity of the electrical system by the electrical accessories and battery. When all electrical components are turned off, it reflects only the amount of charging current demanded by the battery. Hydraulic systems. There are multiple applications for hydraulic use in aircraft, depending on the complexity of the aircraft. For example, hydraulics is often used on small airplanes to operate wheel brakes, retractable landing gear, and some constant-speed propellers. On large airplanes, hydraulics is used for flight control surfaces, wing flaps, spoilers, and other systems. A basic hydraulic system consists of a reservoir, pump, either hand, electric, or engine-driven, a filter to keep the fluid clean, selector valve to control the direction of flow, relief valve to relieve excess pressure, and an actuator. A mineral-based hydraulic fluid is the most widely used type for small aircraft. This type of hydraulic fluid, a kerosene-like petroleum product, has good lubricating properties as well as additives to inhibit foaming and prevent the formation of corrosion. Landing gear. The landing gear forms the principal support of an aircraft on the surface. The most common type of landing gear consists of wheels, but aircraft can also be equipped with floats for water operations or skis for landing on snow. The landing gear on small aircraft consists of 3 wheels, 2 main wheels, one located on each side of the fuselage, and a third wheel positioned either at the front or rear of the airplane. Landing gear employing a rear-mounted wheel is called conventional landing gear. Airplanes with conventional landing gear are often referred to as tailwheel airplanes. When the third wheel is located on the nose, it is called a nose wheel, and the design is referred to as a tricycle gear. A steerable nose wheel, or tail wheel, permits the airplane to be controlled throughout all operations while on the ground. A tricycle gear airplane has 3 advantages. 1, it allows more forceful application of the brakes during landings at high speeds without causing the aircraft to nose over. 2, it permits better forward visibility for the pilot during takeoff, landing, and taxiing. 3, it tends to prevent ground looping, swerving, by providing more directional stability during ground operation, since the aircraft's center of gravity is forward of the main wheels. The forward CG keeps the airplane moving forward in a straight line rather than ground looping. Tailwheel landing gear aircraft have 2 main wheels attached to the airframe ahead of its CG that support most of the weight of the structure. A tail wheel at the very back of the fuselage provides a third point of support. This arrangement allows adequate ground clearance for a larger propeller and is more desirable for operations on unimproved fields. With the CG located behind the main gear, directional control of this type aircraft becomes more difficult while on the ground. This is the main disadvantage of the tailwheel landing gear. For example, if the pilot allows the aircraft to swerve while rolling on the ground at a low speed, he or she may not have sufficient rudder control, and the CG will attempt to get ahead of the main gear, which may cause the airplane to ground loop. Lack of good forward visibility when the tail wheel is on or near the ground is a second disadvantage of tailwheel landing gear aircraft. These inherent problems mean specific training is required in tailwheel aircraft. Landing gear can also be classified as either fixed or retractable. A fixed gear always remains extended and has the advantage of simplicity combined with low maintenance. A retractable gear is designed to streamline the airplane by allowing the landing gear to be stowed inside the structure during cruising flight. All aircraft have a requirement for essential systems, such as the engine, propeller, induction, ignition systems, as well as the fuel, lubrication, cooling, electrical, landing gear, and environmental control systems to support flight. Understanding the aircraft systems of the aircraft being flown is critical to its safe operation and proper maintenance. Consult the AFM POH for specific information pertaining to the aircraft being flown. Various manufacturer and owners group websites can also be a valuable source of additional information. This concludes your introduction to aircraft systems. We hope you learned a lot. Please help us spread the word about Pilot Training System, and we look forward to further servicing your flight training needs.